Hello, everyone. In this video, we will start our discussion about the Algol language. So far, we have talked about the BNF, we have the Fortran, and now it's time to go over the second generation languages and understand exactly what the difference and how the languages evolved over time. So in this video, we will talk deeply into Algol. In a previous video, we had a brief history about Algol, why it was developed in the first place. Now we want to go ahead and understand how the Algol language was actually like the different part of the language, how the language looks like, and how it is different from Fortran. So to quickly just to recap the objectives of Algol when Algol was first developed, the language, they wanted to develop a language such that it would be very close to mathematical notation, which was very similar to what Fortran was at the beginning. And it should be useful in publication to describe algorithms. So it should be easy to describe algorithms in when you publish and you have read it in paper. And it should be mechanically translatable to machine code as well. So these are the main objectives of Algol. I'm just reiterating them here in order for us to remember what was the goal of Algol. And you can go back to the history video to understand those objectives in more details. So how the language is exactly organized. So the language is hierarchically structured language, and it allows to have nesting. With the introduced that, Fortran did not allow any nesting at all. And the nesting and the hierarchical organization is one of the main characteristics of Algol. And the nesting itself can be used even to control structure. So for example, the example that we have here is you can basically have an if condition, and then you can have a for loop nested inside the if condition, and so on. So that allows to decrease the number of go-tos required. You don't have to have a lot of go-tos inside the language now, because the control structures allows to have nesting. You can have if condition inside the for you can have if condition, and so on, which something did not exist in Fortran. So now Algol introduced that and made it different than how it was before in Fortran. Also, one important thing that Algol introduced as well was the reserved words. So there are certain reserved words that you cannot use to declare variables or use them to name your functions, which was something not existing in Fortran as well before. Algol introduced it here. So it makes it much easier to work with the language. And if you see the languages that are common now, like C++ or Java or Python, all of them have reserved word that you cannot actually be using to name your variables or your functions. Now, what about the constructs? The constructs can be exactly similar to Fortran, so they can be declarative or imperatives. In Algol, you can have variable declarations, and you can have integers, real, and boolean. So they introduced the boolean as a data type. And Algol only allowed those three different data types to have: integer, real, and boolean. And arrays in Fortran, arrays in Algol were actually dynamic arrays, not static arrays. And we're going to go over that into more details later on. The arrays as well in Algol were allowed to have a bound that has to be 1. So you can have a negative bound like -50. So you can say data of -25, or you want to access data of -20 or data of -30. That is something that was allowed in Algol and was introduced in Algol. Fortran did not have that. And also, Algol introduced a switch statement, which is similar to the Fortran computed goto. What about the subprograms? Now, the subprogram, in order to declare the subprograms, they use a specific keyword, which is the keyword procedures. And the procedures can be typed, so they're gonna behave similar to functions, and they cannot be untyped. And the typed is like a Fortran functions exactly, that they are expected to produce an output. And the untyped are basically similar to the Fortran subroutines, which can produce multiple outputs or no outputs at all. Okay, so that is exactly the difference between both. You can have a typed and untyped. Now, what about the imperatives construct? The imperative construct, the computational ones, you can have assignment statement. So the assignment statement in Algol became to be variable, and then the colons here, and then equal, and then the expression. And you can have operators like arithmetic operators, plus, minus, and so on. You can have relational operators like comparison, equal or not equal, less than and greater than, and logic operators as well. But something very important that you notice here, that the assignment statement, it changed it in Algol, so you can have the colons here and the equal, and not just the equal statements. And basically because Algol wanted to have the assignment statement to be different from definition and basically from comparison. So if you have I equal I plus 1, they wanted to act different from this one here. So this is an assignment statement, the one on the right here, and this one would be a comparison statement. So they wanted to have the difference between both. And that bring us back to the syntactic consistency principle, that things that look similar should be similar, and things that look different should be acting different. Also, the control flow in the Algol, all imperative constructs alter flow of control, except the assignment statement. So you are expecting to have, like if you have if else statement, then it's really changed the control flow of the program. You have for loops, also changed the control flow of the program. And the for loops in Algol basically were used to replace the do loop in Fortran. However, one important aspect of Algol, and which was one of the drawbacks actually of Algol later on and created a backfire later on, is they did not allow, the language itself does not allow input-output constructs. And the I/O part was left to be handled by platform-dependent library calls. They are expecting that other people are going to develop the libraries and add them to Algol. And unfortunately, that was very bad aspect in Algol that later on made Algol not that famous language, or not being used that frequently. By the time the developers understood that the drawback of that, and by the time they added it, unfortunately, other languages were developed and people moved away from Algol. So this is one of the reasons that Algol is not being used as frequently as other languages. So what about the name structures and how exactly the naming happens in Algol? So Algol introduces something very important called the compound statement. And the compound statement is simply a group of statements that are together, and they do not include any declaration. So inside a compound statement, you really do not declare any new variable. And in Algol, you can have one statement, and you can use also the compound statement replacing one statement. And if you want to use compound statement, you basically use a begin and end, and then you can write as many statements as you want between the begin and end. So this is a compound statement and this is single statement. And that's very important because you want to decide the beginning and ending of the for loop. Think about it similar to curly brackets in neural languages, or the indentation in Python, how Python use indentation to make sure that those statements are a group of statements together. One thing also in Algol about the statements is you can have the body of a procedure to be just a single statement. It does not have to be a group of statements. Okay, so let's move on about the naming. So how does the name binding happens in Algol, and when exactly the name binding happens? So in Fortran, it binds a variable to a single memory location statically. So at the beginning, when you execute the program, this is really happening statically. You have a specific location for that variable assigned to it. So when Algol was developed, they did results and they basically studied it. And a lot of research has been done on name structures. And they found out it's very problematic in Fortran how the data and how it was structured and how the name binding happened inside Fortran. So they found it problematic because of how the sharing data between subprograms would happens. The parameter passing mode that it actually had causes issues as well. How the return values happen and having the dynamic arrays. So the result of that research that was included in Algol 60, the result of that to generate something called block structure. So the block structure is basically you have a as well begin and end. So you have a block, a group of statements, and the block start with a begin statement and end with an end statement. So similar to the compound statement. The difference is within a block, you can have declaration, but in compound statement, you do not have declaration. And all of that is different from what Fortran had. So Fortran, what it had local and global declarations only. And if you wanted to redeclare and you want to share things between procedures, you would use the common block in order to share. So in Fortran, in Algol, that was a change. In Algol, that was changed to something different to make it much better in sharing and how the variables were declared and the scopes of variables. Now, why do we need scopes? Why do we need to have the whole thing about blocks and the scope of variables and the declaration where it happens? Because when you have the scopes of variables and scopes of your declaration, that reduces the context programmers have to keep in mind where those variables are accessible and how, and also it makes it easier to share variables between the different procedures. And we're actually going to see that as well. It makes it much easier to understand and maintain the program. And one important thing is the scopes also reduces visibility of names. So you only declare variables only when needed, and then they're used and then removed, which is different from Fortran, because in Fortran, the variables were declared statically at the beginning of the program. So they're always going to stay there. Think about them as global variables. Everyone can access them. And that takes also a lot of the space of your memory. But in Algol, because of the scope, then you basically declare the variable when it's needed. When it's not needed, it's going to be removed from the memory. And when you have nested blocks, when a block inside another block and so on, it would be, you basically have a block inherit the visibility of the variables in the bigger block. And we're going to have more examples about that so that it'd be more easier to understand this exactly and what we mean by that. So we know that the common blocks, if we want to share variables between different functions in Fortran, creates a lot of error, right? We know that. And the blocks option in Algol that was created, it provided a better way. So to understand that, we have here a block called, we start with begin and with end. We declare an array here, and this array, we declare it inside our bigger block here. You can see, and then we have our different procedures. Now, since those procedures are declared within the same block of that array, then basically that array will be accessible by those procedures. So you see that because they are within the same block, now you can access that array. We don't have to use the common blocks that were used before by Fortran. And that allows us to go back to the impossible error, which means that how this related to it. If shared variables are declared once and only once, there is no way actually to make a mistake when declaring and redeclaring and redeclaring them. And that's the way it was used in Fortran common blocks. So now it is different here in Algol. However, that also brings its own issue that blocks provide indiscriminate access to the data. So since function must be accessible to the user, the data structure must be accessible to the functions, then the data is also accessible to the user, and that violates the information hiding principle. So the user doesn't only have access to the functions, the user as well has access to the data itself, and that violates the information hiding. So even though it comes with its own advantage over Fortran and solves a big important issue in Fortran, it comes with its own problem as well. Hello, everyone. In this video, we will continue our discussion about the Algol language. And specifically, we are going to talk about the contour diagram. So by the end of the last video, we talked about the block structure in Algol and how it is used in order to group statements and sentences in order to define blocks of sentences related to a for loop or an if condition or a procedure, and how it is combined with the keywords begin and end. So in this video, we will talk more about the block structure, its effects on the scoping of variables, and the dynamic and static scoping. So contour diagrams are a way of showing the relationship and how the variables are defined in the different blocks that we have. And basically, to in a nutshell, inner blocks, if you have a contour diagram, inner blocks in a contour diagram implicitly inherit access to all the variables, and we're going to show that in the diagram as well. So they're going to inherit access to all variables in immediately surrounding block. And names declared in a block are local to the block, and names declared in surrounding blocks are non-local. So basically, we are defining the scope of the variables and the names that are defined and declared. So based on which block they are declared, they are either local, non-local, or if they are declared in the outermost block are called global. And we are going to use a contour diagram to show exactly the visibility of the different variables and what each blocks see exactly regarding which names and which variables. So to have an example here, this is an example from the book, so you can go back and return back to the book if you want to understand more about this example. But what we have here to the right, we have our program, and to the left, we have here the contour diagram for our Algol program. So basically, we have a for loop that we are defining here. Inside the for loop, we have a sum variable. And we are beginning our block here. So we have the begin, we have the end of the first block. And then after that, we have a begin and an end of a second block. We also have this block right here that is defined with another begin and end. So we have 1, 2, and 1. So one block. So this is the outer one. We have a second block here. And we have a third block. And the drawing to the left right here shows the nesting of those blocks. So you have the inner block, the innermost block, the outermost block, and the one in the middle. So, and it shows exactly what each one sees and what each one declaring. So inside the innermost block, we have the real variable val that is being declared in the innermost. And the innermost block is the only one that's going to see this variable. None of the outermost blocks were actually going to see it. And at the same time, the innermost block will actually see all the variables or the names that have been declared in the surrounding block. So this block right here will see all those variables, data, sum, average, and I. So if you can see, here's the I. The n is declared all the way up here. So this is the n that we have. The data also, we have it. So basically we have the inner one here. It has the data that is being declared. It has the sum average being declared. It has the I that is being declared. And the outer block here actually has this I being declared, not this outer I in the for loop. It is actually this variable, this name that being declared. So this is the outermost one declared in, and then the one in the middle, we have data, sum, average, and I, and then the innermost one will have the val being declared. And basically, if we call this one block 1, the second one block 2, and the third one block 3, then block number 3 here, we see val, I, average, sum, and data, and also we'll see n. The block number 2 will not see val, but we'll see data, sum, average, and I, and we'll see n. And then the outermost block number 1 will only see the variable or the name n. So this is basically a contour diagram, shows you what the scope of the variables, what the scope of names based on the begin and end of a specific block. So we just have a second more example here with more of a nested environments. So we have here the blocks being more defined so you can actually see it. So we have the begin and end, the outermost one. We have the function here, procedure here, cost here. We have another procedure, F right here with its own begin and end was defining an array. We have a second one here with an array being defined with another block, begin and end. So the array count here is going to be, we are referring to this block. So if we call the blocks again, let's give them numbers, 1, 2, 3, 4, and 5. So this is basically number 5 being defined. The outermost one is basically number 1. And then number 2 is our procedure, cosh is right here. And number 3 is our second procedure, F, right here. And number 4 is the array, the block about the array being defined inside the function number here 4. Okay, so the function is right here. We have the other function F here. So both of them being defined within the scope of block number 1. And inside each one of them, the cosh here has X being defined. So the cosh function will be able to see that procedure, and then the F procedure or the cosh procedure will be able to see the variable X, and the F procedure will be able to see X, Z, and Y that have been declared inside of it, and also going to be able to see, and then we have the array A that's going to also be able to see the Z and Y being declared in the procedure. And lastly, that block we have here count that will be able to see. Basically, it is declared within the outermost block that this is a block that's actually going to see it. So whatever block, inner block that is declared in the outer block, the inner block will see whatever declared in the outer block, but it's not going to be able to see whatever declared inside the other block. So basically, that's also defined the scope of the different names that we have. So what does this mean? That the count, basically, we're not going to be able to see array A that has been declared inside the procedure F. So now when we decide the scope of variables within the block itself and what is actually what values it actually gets. So what value do we actually give to our names inside the blocks? We have to go to something called dynamic and static scoping. So you can either pick dynamic scoping or static scoping, and we're going to give an example to better understand the difference between both. So static scoping, in static scoping, procedure is called in the context of its declaration. So basically the environment of definition. And scope structure is determined at compile time. And we're going to see an example to better understand that. And that's what happens in languages like Algol. In dynamic scoping, the procedure is called in the context of its caller. So wherever it is called, not where it is defined. So in static scoping is basically about where you first define and declare the function. That's how we're going to get the values for its variable. In dynamic scoping, the procedure basically is going to be the context of its caller. So whatever variables being declared within the context of its caller, then it's basically going to use that. Let's call the environment of the caller, the caller, and the scope structure is determined during runtime, not during the compile time, because it's going to change. And some languages that use dynamic scoping is Lisp, which we're going to talk about later. So let's have an example here of a program and talk about the dynamic scoping and static scoping and how that actually affects the scope of variables and how that affects our control diagram. And we're going to see the control diagram for both static scoping and dynamic scoping. So we have a very simple program here. We have two blocks. So we have block A, and then we have block B. In block A, we have the integer, the name M declared. We have procedure P, and then M is used to be inside the procedure is set to be 1. And then we have block B being declared. We have M being declared inside the block B. And then inside that, and the block basically end, and inside that we have an inner call for P, and then outside block B, inside the outer block A, we have a call for procedure P. So P being called twice, one inside block B and one outside block B. So, and the M variable being declared as well twice. It's declared one time inside block B, and another time it is declared in the outer block A. So when we have dynamic scoping and we want to exactly see what the caller P, what value for M is actually going to maintain, and basically what value it's going to see. So this is our block A, and then this is our second and this is basically our function P or procedure P. And this is drawing here of the invocation of P from the outer block A. So this is basically, we're talking about this outer call. So now we are talking about the outer call for the procedure P. So it is being called from the block A. And A has two things being declared, the name M and then the procedure P. So when we call P, it's basically going to basically set up the M equal 1 to the variable or the name M that it can see in the outer block. So when we call about M here, then basically we are referring to the outer M, because basically P is being called inside the block A. So pay attention again. P is being called from inside the block A. So the M inside here will be referring to that M we have. Now, if we look at the inner call, the P, the inner call, so this is the invocation of P from the inner block B. So we have here's our outer block A, and then we have our inner block B, and then we now calling the P from inside the block B. So since we are calling P and we have dynamic scoping, so since we're calling P from inside the inner block B, what is going to happen is basically anything that's going to be P is going to be called from the environment of the caller. So whatever is going to use from inside, whatever variables is going to use, whatever names is going to use, it's going to be basically from inside the block it is being called in. So you see that P actually, when it's called from the environment of A, then basically that is what it is using, whatever is declared in A. When it is now inserted inside the block B and being called from inside the block B, then its context and the name that it's going to use are going to be used from inside B instead of being used from inside A. So that's dynamic scoping. You can see that whatever P is being called, then that is where P is going to maintain the names, and that's P we're going to be using. So the M that we're using here is basically referring to that closest M, not the outer one in the outer block. So, and that's in dynamic scoping. Now, in static scoping, things are totally different. So whether we are calling P from inside the block B, so you're seeing here that P, we are calling it from inside the block B, we are not going to place the environment of P inside the block B. P is going to stay inside the outer environment where it is initially defined. So you can see here that P was initially defined and declared inside the block A. So that's basically, it's going to be called and using things from the environment of its own definition. It's not going to be dependent upon where it is going to be called. So where it's going to be called does not make a difference regarding what names that is going to use and what is actual and which environment it is going to use. So that is the difference between static scoping and dynamic scoping. So that's why static scoping can be done at the compile time, while dynamic scoping need to be done in runtime, because the P environment of the P, it changes, and the name that the P is going to use, it changes based on where it is going to be called, so it dependent on the environment of the caller. So let's have another example here that compares between the static and dynamic scoping. We're not using this example from Wikipedia, and this is not an Algol. This is another syntax. And we have here in our program that we have our X here equal 1, and then we have two function G and function F. Function F goes ahead and declares a local variable X equals 3 and then calls G. And then G, what it does, it basically prints the value of X and then set X to be 2. And then we have here in our program, we're calling F and then we are echoing the value of X. So what is exactly happens when we do that in dynamic and static scoping? So let's start with static scoping. When you have a static scoping, G is being declared in the outer environment right here. So basically G, when it's actually being called, even inside the function F, it will see that the value of X is equal 1. So when F is being called, it's going to call G, and G is going to go ahead and print X. So basically it's going to print x to be equal to 1. And then it's gonna set x to be equal to 2, so it's gonna affect this x we have right here. So when it says echo of the value of x, then basically it's gonna print x to be equal to. So it's first gonna print x to be 1 and then x to be equal to. Now, when we have dynamic scoping, things are now different. So G is being called from inside F. So when we call F, we call basically G. And G now is going to see the value of X to be equal to 3. So when we type the echo of X right here, so it's going to basically print X to be equal to 3. And then it's going to set X equal 2, but that's going to be affecting just the local variable F. So when we return back from F, and we type echo of X, then basically we are going to see the X to be the outer X right here. So it's going to basically print 3 and then print 1. And that with dynamic scoping. So in dynamic scoping, the G will be basically seeing the closest X, which is this one. And static scoping is going to always be seeing this X right here. So you can see that that's different between, that's the main difference between dynamic scoping and static scoping. Now, a very important question about dynamic scoping as well, and its functions, and it's basically advantage. What do we want to have? Like, is there advantage or disadvantage for dynamic scoping, and can we use it? Should we not use it or not? So, advantage of dynamic scoping is that we can write a general procedure that makes use of procedures in the call environment, and we basically don't need to have all names defined in a static context. The disadvantage of that is if call's environment provides a different function than what is intended to be used, and you can see an example for the book for that, then the programmer has to think more about the environment when writing the call. So he has to, every single time that what environment that the function will be used on and how this is going to affect the variables and the names inside the function. So it's basically the programmer has to be much more aware of the environment where the actual procedure is going to be called. So that can be adds a lot of overhead on the programmer when he's writing the program. He has to think about a lot of details. And that brings the question, which one is better? Should we use a dynamic scoping or static scoping? General rule when programming language is being designed is what is natural to humans will actually cause less problems in the long run. So what we easily understand it is going to be cause less problem. And if humans can understand static scoping better, then it will result in higher quality programs in the long run. Dynamic scoping is actually confusing as well. So, and it generally is actually rejected and it's not used in a lot of the new languages. And static scoping agrees more with the program's dynamic behavior. So that's why static scoping is more favored in comparison to dynamic scoping. Yes, dynamic scoping is being used in some languages, but a lot of the newer languages stayed away from using dynamic scoping and went forward to static scoping. So returning back to the idea of blocks and the scoping of variables and where the variables are declared, whether we are using dynamic scoping or static scoping. Blocks permit something very important, which is efficient storage management. If you remember, Fortran used the equivalence blocks, and we showed that how it's not safe because there's no guarantee of the exclusive use of the memory. And basically, you wanted to have the equivalence as well to have that space inside the memory be used by multiple functionalities, but multiple functions. And one of the reasons is memory is scarce and how you not block the memory for a specific procedure for a long time. The advantage of using blocks now is actually permits the reuse of memory. It does not block the memory for a long amount of time. Whatever declared inside the block, whatever declared to be the scope inside the block is going to only be used inside the block. So once the block ends, you can go ahead and delete it and clear the memory. So if we look at our blocks here, so we have the outer block A, we have the inner two blocks, block B, and then we have block C. So since the block B declares array X and the real variable Y, they are going to only be used inside block B, and they're not needed in block C. So once this block ends and we executed that part of the code, so we can go ahead and free the memory and not block them and not reserve the memory for block B anymore. And the same memory can now be used to declare the variable, the name k, and the array m. Because of this memory is not used anymore because of it was declared in block B, and the array x can only be used within this block. So we don't need to keep that memory being reserved for the array x. And that is a huge advantage of blocks and how it is defined. This is allow the memory reuse, which is the problem we had before with Fortran, and now we solved it in another way using blocks. Another something very important to think about as well is the runtime stacks. So basically, how the variables are defined, and since the variables are not in blocks B and C are never going to be used at the same time, then how are we going to store that, especially that when a block calls another function, and that brings us to the runtime stacks. So to keep track of basically what blocks are reserving the memory right now, and if the blocks are not used and basically we exit that block, then we can go ahead and basically discard the variables and we can reuse the memory. So, and in order to keep track of that, we use basically stacks, because blocks entered last will be basically exit first. And that's basically a last in, first out order, which is stacks. And so we can use the stacks to organize our activation record. So when block is entered, is basically activation record is pushed into the stack. And when block is exited, then its activation record is popped out of the stack. And basically, we have the assumption that no local variables are being initialized. And from the previous program that we showed, when we enter A, let's have this example drawing here to better understand it. So when we enter A, N and M are being declared. When we enter B, then we have Y, X, and then N and M. And then when we exit B, we can go ahead and remove Y and X. We don't use them anymore. And we just keep the activation record for the block A. So we keep N and M. And then when we go ahead and enter C, then we can add K and M now to our stack. And then when we exit C, we can go ahead and remove M and K. We are still in block A, so we're still having N and M. And then when we exit A, we go ahead and empty and remove N and M totally. So you see that it's basically a last in, first out structure. So that's why a stack is being used, be the most efficient thing to use to keep track of the activation records for the different blocks. And you can see as well that Algol designer did not include equivalence. And some programmers actually might have asked for it because there is still some advantage of equivalence that programmers have used it a lot in Fortran as well. So in Algol, they focused on responsible design. So instead of providing the programmer with what they asked for, they looked at the root cause of many problems. So basically, they followed the approach: don't ask what they want, ask how the problem arises, and so that they would reduce the problem that would arise. So language designers are responsible for the feature in the language and basically not the programmers. So that's why they're not just providing what the programmers are asking for, they provide what can help the problems not happening in the first place. And that's why they did not provide equivalence and they use the block structure that we have seen. And that brings us to a new programming language principle, which is a responsible design principle. So basically, do not ask programmers what they want, find out what they need. And one of the things that they need is they want to reduce problems that might arise. They don't want to have a lot of issues in the programs and the whole memory is not having unpredictable behavior. So, and that is one of the main principles that have been introduced and used a lot in Algol. Hello, everyone. In this video, we will continue our discussion about the Algol language, and we will learn other aspects of the language. In this video, we will talk specifically about data structures. So we talked before about the data structure in Fortran. So in this one, we will talk about the data structures now in Algol and how it is different or similar to the Fortran and the other data structures that we studied before. So the data structures in in Algol, it included a lot of the things that are very similar to Fortran. So it had a primitive data type, so it had mathematical scalars like in Fortran. The main data type that it's used as well were integers, real, and Boolean. So these are the main data type that it had. And the language Algol did not include complex and double. They were not included. The reason that it's specifically about double, it did not include it because it found that it is platform dependent, because double means double word. So what do we exactly mean by that? So it's really not portable and cannot be used, it cannot be machine independent. So one of the main aspects of Algol is to make it machine independent and make the language itself totally independent of the machine. So that's why the designer of Algol decided not to include the double to make the language itself portable, because we need to know the size of a word is in order to know the size of double. And alternative approach for that is basically we can specify the precision, or basically let the compiler pick the precision for the numbers. The complex, and why the complex were not included in Algol itself, because it's not considered as a primitive type, because it can be constructed using other types easily, basically using two reals. So that's why it's only focused on including primitive types and not a type that can be included or made from other types. So is it really easy to use reals for complex? Yes, but sometimes can be inconvenient and it needs supporting operations. So even though it looks like, yes, we can make it from primitives, but based on the designers of Algol and what design decisions they made, but it's not that easy as we think it could be. And at the end, it's always going to be designer's choice. Is it worthwhile to add the complexity overhead of another type, or will they get enough usage? So when they design Algol, they decided not to include it based on the final decision that they made. What about the strings? Well, it's another data structure that needs full support of specific operations. And Algol designer decided at the end to make strings and use them as second-class citizens. And what we mean by that, it's only allowed to be used for formal parameters. And string letters can only be actual parameters, and we cannot perform any operation at all on the strings. And string can only be passed around in procedure. That's how it can be used. So if you look at it, they cannot actually do anything at all with them. You cannot do any operations. You cannot. You can only use them for formal parameters. So it's really very hard to use a string for something meaningful. So what is the point of strings at the end? Well, the designers of the Algol, when they add a string, they focus on it's going to be at the end passed out to output procedures written in a lower machine language that can basically handle it. So they focus that is going to be based on an output procedure. Remember, Algol does not have input output. So basically it's an extra procedure that basically this is going to be passed to, that's going to be handled later on. And that's how they thought about the string. So in a nutshell, you can look that strings are not really that much supported in Algol, and you cannot do much with them. So also the designers of Algol, they focus on something called 0, 1, or infinity rule. So basically, they wanted to have the programmers not to remember a lot of numbers. If you remember, for example, in Fortran, they had specific numbers with certain rules. For example, the identifiers can have a max of 6 characters, and they are at most 19 continuation cards. And arrays can only have at most 3 dimensions. So if you look that, there are so many numbers that the programmers have to remember. So they decided that something can either be 0, can be 1, or it could be infinity. There's no limitation on its dimension. And that's what they basically followed. And that basically, because they wanted to have regularity in Algol, so they don't want to have a lot of exceptions. They want to have the user, the programmer doesn't have to remember a lot of numbers. So, and that's what the 0, 1 infinity principle about. An example for that in Algol, identifier names should be either 0, 1, or unlimited length. And of course, 0 and 1 don't make much sense. So what exactly does the 0, 1 infinity principle say? It says that the only reasonable numbers in programming languages and programming language design are 0, 1, and infinity. Again, to make it much easier for the programmer, not having to remember a lot of numbers. So it's going to be either 0, 1, or infinity. What about arrays? Arrays and algols are generalized, and they basically can have any number of dimensions, returning back to the 0, 1 infinity rule. The lower bound, also one important difference in arrays in Algol in comparison to Fortran, that the lower bound can be number other than 1. In Fortran, the lower bound had to be 1. In arrays in Algol, you can have a negative number as the lower bound for the arrays. And it is more intuitive and less error prone than having a fixed lower bound. Another important change in Algol that the arrays are dynamics. And what we mean by that they can be given, the bound for the array can be given as expression, and the expression can basically allow to be recomputed multiple times every time the block is entered. So basically the array size is not fixed, it's not static from the beginning of the program. If you remember in Fortran, you have to specify the size of the array, and sometimes the size of the array you can't really define at the beginning of the program. So you end up creating an array with a huge size, and that wastes the memory. So in Algol, they decided to remove that, and basically can be an expression that can be evaluated, and that the size is decided based on the evaluation, the result of that expression. One more difference in Algol that it's have a strong typing. And strong typing means that you cannot manipulate the data in another way other than what it defined for it. Meaning, if you define an integer, you can use that data as an integer. You cannot really manipulate it to use it for something else. And why Algol wanted to go this way? Because they wanted to prevent programmers from doing meaningless operations on data. And we want to make this very clear that this is really different from having a legitimate type convergence between two types. So basically, for example, you want to add integer and real, so you're changing the integer to be real to be adding the two together. So this is still allowed, but what they did not allow is the data itself when it's stored inside the memory. If it's an integer, you will have to treat it as an integer. You cannot treat the data as in real. In Fortran, that's different. So maybe remind you a little bit of Fortran. Fortran was a weak typed language, and it permits adding something like the whole earth constants, if you remember when you talked about the strings. And when we had equivalence, it allowed the same memory location to be used and stored different data types in the same memory location. So you can, one area it's using it, one procedure is using it as that memory block, using it as an integer, and another is using it as a real. So that was allowed in Fortran, that's not allowed anymore in Algol. And that creates security and maintenance problem, and intentional type violations is not portable as well. Okay, and exception for that is system programming language C. When we talked about strong typing, the language C would be exception for that. And it because it treats the memory cells as raw storage without regarding to type. So the language C itself behaves differently than that. And you're going to see that some languages decided to follow the behavior of having a strong type, and you cannot manipulate the data other than the type that was assigned to that data from the beginning. Hello everyone. In this video, we will talk about the control structures in Algol and what are the main structures that were used to exchange the behavior and where the program basically moves forward. So the control structures in Algol have a lot of similarity with Fortran. So there were the primitive statements that are very similar to Fortran's, like the assignment, the control flow that includes if for and go to and other similar statements. And one important thing in Algol as well, that it did not have any input and output operation. So which is really was a bad feature in Fortran, that it did not have any input and output operation. But the others, like assignments and if conditions, for loops, or go-to statements, were very similar to the behavior of Fortran, but Algol as well added more terms that were not present in Fortran, and we'll talk about each one of them specifically. So one important thing in Fortran that the control, one important thing in Algol actually is the controls are more generalized. So for example, when we talk about the F statement. So Fortran had many restrictions. So for example, if you have if condition, expression, and then a simple statement, the statement were basically restricted to go to, call, or assignment. That's what you're going to have next after the if condition. In Algol, it created more of generalization. It removed the restrictions. Basically, all statements are allowed, even if another if statement inside the if statement body. And also, it added the else keyword to address false conditions. And all of that was not added in Fortran. You only allowed go to or call all another assignment. So that's very limited in Fortran, which was finally removed in Algol, making it similar to the behavior of the regular languages that we actually use nowadays. What about the for loop? So the Algol introduced the for loop that is more general than the Fortran's one, the do Fortran's one. So for I equal from 1, you step at 1 until n, you would basically do sum equals sum plus date of I. So we made it more of a general, and you have multiple type of for loops as well, not a single type of for loop. So you can have leading decision loop, like for new, guess, improve, you're going to have the for loop and then while and then do. Or you can have same as while loop in a behavior that is similar to the while loop in newer languages. So you have then you guess and then while, and then you have while a specific condition happens, then you will do something, and whatever you want to do is inside the begin and end block. So you can see here that you're going to have multiple statements that you're actually having here, multiple statements surrounded by begin and end. And this is more of similar to the behavior of the while loop in the languages that we have right now. So it's much more general than the Fortran's one. Also, the for loop, there are many different types of the for loops, and it's so general that you can actually do a lot of things with it. So for example, here it's saying for I equals 3, 7, and 11. So when I is equals 3, 7, and 11, you want to do step 1 until it reaches 16. And once the I reaches 16, then basically go ahead and divide the I over 2 until the I is greater than 1 or equal 1. And then after that, you do 2 steps of I until it reaches 32. So you see that you have multiple options inside the for loop. You're not just looping through 1, 2, 3, 4, 5. You're basically doing multiple options. Like the loop itself is not consistent. You can basically go do 1 step and then do some division, and then you do 2 steps. And while you're doing all of that, you're actually going to print the value of I. So what is going to happen at the end? What is going to be that? Basically, the output is going to be, you're going to print I. So you're going to print I equals 3 and then 7. And then after that, when it is 11, we're going to go ahead and do step 1. So we're going to keep on stepping 1 until it reaches 16. So we're going to print 11, 12, 13, 14, 15, and 16. Once we reach 16, we're going to go ahead and execute the second part of the for loop. So we're going to go ahead and divide the 16 by 2. So we're going to have 8 and then 4. 2 until we reach 1. Once we reach 1, we do the third part here, which is basically two steps in I. So basically from 2 step I until 32. So going to be 2, then 4, and then 8, 16. So basically doubling it, basically multiplying it until we reach the number 32. So we're multiplying the I until we reach the number 32, and all of the time we are printing I. So you see, it provided so much options that some of those options might be too much that we actually don't need to use them. So basically, it's really very general. It can be, you can loop through lists, you can have conditional expressions, you can even have combinations of the above. So you combine a lot of both, like what we have seen so far. So it's extremely general. You can do so many things with a single for loop. And that give us something in the language called Baruch, basically features, meaning that you create a lot of fascination and a lot of options and a lot of feature in the language that you actually don't need it. You create a lot of features with a specific construct inside the language that you actually don't need it. And they did that because basically why they did it with Algol, because they could do it, so they did it. And they were focusing on getting as much as possible away from assembly language. And if you actually can Google as well, Baruch, and try to understand what the word means, but it's basically a type of art that existed in the 17th century. You want to have something, add a lot of complexity, make it so much artistic, so much features being added into it, that at the end we don't actually need to use it. We don't actually need to have it. And it creates a lot of complexity in the language itself when we have such many features. And a lot of languages afterwards, they did not really add that much features in the language or in the different construct that they had. So they moved away from that. But Algol actually, unfortunately, they moved into having so many features associated with the for loop and specific other construct with the language too. Also, returning back to our control structures, one of the things that Algol had as well with the handling cases, the switch. So it had a switch statement, and how it had the switch statement, it's created a switch. Basically, you have like an array that contains multiple values, full-time, part-time, and hourly. So you have those values similar to an array, and then you use a go-to statement, and based on the value of I, you would jump to the different labels. And once you handle the full-time case, you basically jump to the done keyword. So if you can notice here, Algol still allowed to use the go-to. So Algol did not remove the go-to. The go-to is still part of Algol, similar to Fortran. And even though a lot of languages, they provide a lot of other control flow structures, like the for, the while, the do while loops, the go-to is usually still part of a lot of the languages. It's not totally being removed. Algol still give the go-to just in case it was needed. And if you think about it, it's more of an elaboration on the computed go-to and Fortran, so it's very similar to it. It's a bit confusing since switch, go-to, and labels can be anywhere in the program. It's not really concise in a specific part of the program. It could be anywhere in the program, so that the labels can be very confusing. That is not defined, has to be next to each other. And the label list can contain as well conditionals. Neural language had moved away from that behavior of the switch. It used switch cases, so the cases has to be defined underneath the switch statement. So it's a nice step if you think about it this way. It's moved away from the computed go-to into a better situation, but then the newer generation languages try to create a similar behavior, but create more constraints so it wouldn't be as confusing as it is right now in Algol. One of the things of Algol when they defined and when they worked with the control structure, the Algol was designed around regularity. Anything that you think you ought to be able to do, you will be able to do. And you wanna go ahead and remove inexplicable exceptions from the language, and that is more of an elaboration on the 0-1 infinity principle that we talked about before in another video. So they wanted to have, like, you should be able to do this, then we have to go ahead and provide it for you in the language. So the begin and end that we talked about before in Algol and Algol in a previous video, how they started at the beginning when Algol in 58, all control structures should be allowed to have any number of statements. So that's when Algol 58. All control statements were considered an opening bracket with corresponding closing bracket, like if and if. In Algol 60, and largely due to the BNF notation, they realized that one bracketing mechanism is basically not enough for all. And that's why they defined the begin and end bracketing. They define it that one mechanism is not going to be sufficient, and that's why they defined the begin and end. It allowed them to define compound statements and make one statement out of a group of statements. And it allowed anywhere in a single statement as expected. So you basically can use the begin and end. You can have compound statement anywhere, a compound statement anywhere that you can have anywhere you can have a single statement using the begin and end bracketing system. So example for here, you can have a for loop with one statement, as you can see here, or you can have a for loop with multiple statements, but you have to add the begin and end to say that they consist of multiple statements, and those statements belong to the for loop. If you don't do that, then the second state might not be belonging to the for loop, might be considered not belonging to the for loop, could be considered not belonging to the for loop, in other words. We have to keep issues in mind, a couple of things in mind about the begin and end. It's really easy to omit the begin and end, especially when a single statement is used first, then another one is added to the program. And especially in the case of well-indented code, like the example here, if you see the begin and end is removed, we have two statements, but only one statement is going to be considered as part of the for loop. So this is more of a maintenance program, and a good convention is always to use bracketing. You always use begin and end, even if you know that you only need one statement, but just a good practice is just to always have a begin and end bracket being added to your for loop or other structures you have. Also, the begin and end has more of a double duty. So they are used for compound statements, and they are used as well for blocks for defining nested scopes, as we have seen when we talked about the contour diagrams. And when they are used as blocks and not as compound statement, they can include definition in addition to the statement. So what is the difference between then when the begin and ends are used for compound statement, and how are they when they're used for blocks? Remember the compound statements, you cannot have definitions inside the compound statement. When the begin and ends are used as within a block, you can have nested scopes, and you can have definitions. You can define new variables. You cannot do that in compound statements. Now, is there a difference behavior when the compiler handle the begin and end, whether compound statement or blocks? Yes. So when you have a compound statement, you're using begin and end for a compound statement, you do not need an activation record. If you remember an activation record, you keep like the information about that block when you try to enter another block when you're within a certain block, if you remember that, because you don't want to mess up the variables that you defined before inside the block. So you use an activation record in order to keep information about the block before you move into another block. With the compound statement, you don't need to have an activation record, and that result is the compiler must determine whether the begin and end that are used for declaration, or they are used to generate block entry code, because the behavior is going to be different, whether it needs to generate an activation record or it doesn't need to generate an activation record. And the introduction of the begin and end block allowed to have more of a structured programming, because of the compound statements drastically reduce the number of goto that we needed to have. So more of goto is being removed. If you remember in Fortran, the goto was the workhorse for the control. In Algol, that's not the case anymore. So now the Algol allowed to have more of a go-to list programs, and those programs are much now easier to read than how it was in Fortran. It was much harder to in Fortran. That some people decided to experiment with abolishing go-to totally and not using it at all. And Dijkstra suggested that go-to statements are actually considered harmful, because it's difficult to read the programs that you have go-to, and the static layout on a paper, if you look at the program, if you want to compare it to the versus runtime, the operation of the program, what is the result? As mentioned before, the languages still have the go-tos, but we don't use them. So we have seen that the Algol already have the go-to, but we don't use it that frequently. It's better to use other ways and other mechanisms to change the control flow in the program rather than using the go-to, because it's very confusing creating that spaghetti programs at the end. And that reminds us of the structure principle, that the static structure of the program should correspond in a simple way to the dynamic structure of the corresponding computations. So when you look at the static structure of your program on a piece of paper, it has to correspond to the same behavior that it would have in the dynamic structure and the computation that's going to happen. So how it looks like should help you understand how it's supposed to behave. And that what having a program that don't use goto that frequently allowed to create such a structure in the program when you are designing and working with it. Now, since we said that Algol allowed to have go-tos, that might have an issue with the blocks that we have. We have begin and end. That you might actually end up having an out-of-block go-tos. And what do I mean by that? If you look at our code here, we have two blocks. So we have the block B, we have block A. So block A start begin and end here, and then block B has begin and end here. Now, the go-to that we have here is as an exit, go to the exit, and the exit you see it's outside block B. If you remember when we talked about the blocks, that whenever you enter a new block, you need to have create an activation record inside the stack to keep track of all the activation record, the blocks, the variable that you declare inside your blocks. Now, what would happen when we have a go-to that goes outside of the block? So the go-to, the exit here, we didn't end yet that block. The block is still the block, we are still inside that block. We didn't, the compiler didn't yet find the end matching to the begin that we currently have. So when we have this exit, what is going to have to the activation record for block B? So since the program now continues in different block, we need to pop the activation record, and that makes it, the go-to makes things more complicated, as you can see, because of we can jump to outside of blocks and not we don't have to stay in the same block with a go-to statement. And that's going to even make things worse. We're going to talk in another videos about procedures, and we're going to talk about recursive calls and recursive procedures in Algol. But when you have a recursive procedure like this one, and we have a go-to statement and you have activation record. So if you suddenly decide, or the program at some point when it evaluates, it can now call the go-to out, and you see here the out is outside the procedure, totally outside that, and we have actually the procedure called right here. So when we actually call the go-to out and we jump right here, you actually have all the activation record for all the recursive calls that we have. So when we go to out, then the program has to to know that we exit the recursive call, and that it has to pop out all the activation record for whatever number of recursive calls that we already did. Because this function here, recursive call 25 times, then jump to out. So the compiler has to pop 25 activation record. So that is really data dependent and cannot know at the compile time. And implement the go-to as call of, basically it has to be implemented as call of runtime routine. But you can see how go-to basically complicate things when you have other features of the program, of the language being added, and now the two having a go-to inside a recursive call complicate things at in the compiler understanding about the activation records. And that showed us something called feature interactions. And what we mean by that is you have go-tos, which are very simple. We have recursion, which is very simple as well. However, when we combine both, we allow go-tos with recursive calls, things become very messy. In theory, each feature actually must be tested with every other one to avoid unintended consequences, like what we have seen so far. So we have to see all the features that the language provide, and we have to test them together to see the consequence of interactions. So if we have 100 features, then every pair that's going to have 10,000 combinations. What about every 3, then we're going to have 1 million combinations, and so on. So it's very complex to go ahead and try to test the features together in order to understand the behavior of the different features when the feature interactions interact together. So you see that it's not something very simple as we can think it is, even though the two features separately, the go-to feature separately is a simple one, the recursive feature separately is a simple one, but both of them combined create a very messy behavior. Hello, everyone. In this video, we will continue our discussion about control structures, and specifically, we'll talk about the procedures and how they are defined in Algol. So in Algol, it defined procedures similar to Fortran, but they added a very important part to it, which is recursion. So recursion was not allowed in Fortran. You cannot have recursive procedures in Fortran. But recursion is very important because a lot of operation in mathematics actually includes recursion. So we need to have it. So for example, if you have a factorial operation right here, then basically we're gonna say factorial n factorial, then it's basically equal n multiplied by n minus 1 factorial, and then for n greater than 0 and 1 if n is a 0. So you see that it is a recursive in its nature. So a goal permanent recursive procedure. So basically can define the recursive function in a goal, and that's gonna be the definition. We're gonna have, of course, a base case. So when we reach the beginning, we basically return back from the program. So n equals 0 is called basically the stopping condition. What we use it as well nowadays, we call it the base condition. So what happens to local variables in recursive call? So we have to look at the activation record, and we have to look at when we do the call and we jump to another call, what we need to do. So when we have factorial 3 is called, for example, then factorial 2, then factorial 1, then we have factorial 0. What location holding 3 will be would the location holding 3 will be overridden? Yes, if we are using the same activation record. So the solution for that for recursive call is that we're gonna have create a new activation record for each invocation of the factorial function. So we're gonna create a new activation record. We keep that activation record in the activation record stack. And once we return back from a specific recursive call, then we go ahead and pop out that activation record associated with that recursive call. So we need to have activation record for each function call. We treat it as a regular function call. So whenever you call a function and jump to a second function, or whenever you call a procedure and jump into a second procedure, then you have to create an activation record to keep track of your the previous function, the previous procedure call. Now, we have to think about how Algol actually does parameter passing. So what different types of modes that are supported in Algol? So Algol provides two modes for parameter passing. It can have pass by value, or it can have pass by name. The two modes attempt to distinguish between having basically input only allowed, or we can have input output parameters. So basically if it's pass by value, then basically you have input only allowed, and you have input output parameter, then basically that's pass by name. Pass by value, if we want to say that we are passing by value in a procedure in Fortran, in Algol, then basically we use the keyword value. So that is how we define it in Algol. We use a keyword value in order to define that this is a pass by value. And in first part of pass by value results, basically in Fortran, what we do is the actual copied into variable corresponding to the formal. And it is very secure because local variables cannot be overwritten by the actual parameters. So we just do copying it, and we send it to the procedure. We never actually send the actual itself. We never send it to the procedure itself. So we don't have any worry about the actual parameter being overwritten by the procedure itself. And which is very similar, which is what Algol does as well. So this is what happens in Fortran, and Algol still follow the same behavior as Fortran and does the same thing as Fortran. One important thing as well, it does not allow output parameters, so you can only have input parameters, and you cannot basically use it to, you want to have return some result, then basically you cannot use a pass by value in that case. It is, of course, inefficient in arrays because you have to copy the actual into the formal. It's very secure, but copying with an array, the array is quite long and quite large, especially specifically if you have a large array. Doing the copying operation from the actual to the formal is going to take a lot of time. So it's not very efficient when you're working with an array. Because keep in mind that, well, we work with activation record, so copy must be made of an entire array in activation record, and of course the copying will take some time. So that brings us to the pass by name then. Pass by name is based on substitution. So consider the function that the procedure that we have here. It's an increment procedure. It takes an integer variable in, and then basically increment that variable. So what happened when we actually call increment I? We're actually sending the I here and the output parameter that will affect I, not just local n. So when we send the I, they're actually gonna replace the n that we have inside the procedure itself. So the I itself will gonna be affected and the I itself will be incremented. So acts basically like I is substituted for n, like you remove n and you put I inside that, and then you, as if you are saying I equal I plus 1 instead of saying n equal n plus 1. So when you send it, it's actually being affected, and that's basically pass by name. So, and that brings us to the copy rule. Basically, the procedure can be replaced by its body with actual substitute for the formals. And what does this mean? That basically what we have seen when we saw that the increment of n, the body of the procedure itself, which is the n equal n plus 1, can be replaced with the actual. So the formals are going to be substituted by the actual. So the n here will be substituted by the actuals we have, which are basically the I, if we're saying I, if we want to increment I, or if we have an array and we want to increment a variable and we want to increment one element of the array, we basically can, that also we send to in the increment function, that is exactly what is going to be incremented, the A of k. So this basically, again, the copy rule, the procedure can be replaced by its body with actual substituted for the formal. So as if we have rewritten the body of the function. But but this is not actually how it is implemented. So even though this is the rule itself and how it seems the behavior it is, this is not actually how it is formally implemented. We're going to talk about its implementation as well in more details. Now, pass by name is actually very powerful. So let's say that we want to evaluate the following. Let's say we're going to evaluate the foreign procedure that we have here. So we're going to evaluate the following procedure by using pass by value, by using pass by reference, and using pass by name. So the same procedure, but we're going to apply pass by value, pass by reference, and pass by name. And this procedure that we have here, it's basically a procedure S. It takes two input here, L, EL, and K. And what it does, basically, it takes the K, and then it replaces the K, assign the value 2 to K, and then EL is going to replace it with 0. And let's say, and that's basically all the procedure, what it does. And let's say that what we're going to do, we're going to have elements of the array, A of 1 and A of 2 being initialized to be equal to 1. And let's say that the variable I is going to be initialized to 1 as well. So, and now we go in the procedure call, and then we're basically sending A of I and sending I to the procedure. And then let's evaluate it by pass by value, pass by reference, and pass by name. So if we have here pass by value, so we're going to basically, what is going to happen to our A of 1, A of 2, and I, they're basically going to stay the same, because if you remember the pass by value, you copy whatever value inside, you send it to the procedure, and the actual parameters are never affected. Only the formal parameters are affected inside the procedure, and your actual parameters are going to stay the same. So A of 1 is going to stay 1, A of 2 is going to stay 1, and I is going to stay 1. Now, when we do pass by reference, we are going to send it by reference to, which is basically the address. So we're going to send the address of A of 1 to our procedure. We're going to send the I as well. So what is going to happen? A of 2, since it was not sent to the procedure, A of 1 is the one going to be changed. So it's going to be changed here, because this is represent the address, the location A of 1 itself. So whenever it changes, it's going to happen here. 0, then basically that's going to affect the original 1 that we're sending here. So basically A of 1 is going to be affected, and A of 1 is going to be assigned to 0. A of 2 is not going to be affected at all, so it's going to be assigned to 1. And I is going to be assigned to 2, because it's sent by reference as well. So whatever changes, K is representing I. So when we change the value inside the K, then basically the I is going to change as well. Now, when we do it pass by name, remember that it's when we say pass by name, as if we are replacing the body with of the procedure with the actuals. So what is going to happen is let's do this. Let's replace it our body here. So the K we have, we're going to replace it with an I. So basically assigning I to be equal to. So that's what exactly we're doing here. E of L is going to be replaced with A of I. So basically replacing it with having A of L basically replaced by A of I. And if you remember A of I, what it is, I is now equal to. Remember the I changed. And the E of L is going to replace A of I. So basically, that means it is A of 2, the one that's going to be affected. So we're going to basically assign A of 2 to be equal to 0. Okay, so A of 2 is being assigned to be equal to 0. So how the arrays are going to be at the end, or the value, the parameters we have, A of 1 is going to stay the same to B of 1. A of 2 is going to be 0, and I is going to be changed to 2. So do you see there is a different behavior for each one of them? The E of L here, we're not just sending the address of the location of A of 1, we're actually as if sending A itself. We're working with it, whenever the I is changed, the A of I is going to be affected and it changed as well inside the procedure. So this is very powerful behavior. Now, how can we implement that behavior? It is implemented by using something called thunks. So, and if we think about it, we want to do the copying and everything. It would be not done at need to compile at runtime, and that's not possible. We copy as we said, copying the compiled code, that would increase the size of the code, so that's not possible. So the solution for that would be thunks, which it behaves differently other than the other ways, which is copying or passing the text. And the thunks, basically, we pass the address to the compiled code. So we pass the address of memory location. The address of memory location is returned to Coli to use as a variable. So the address of that memory location is sent to be used as a variable to the procedure itself, which is different from how the pass by reference. Pass by reference is associated with a specific A of I location, so which is A of 1 in the previous example here. When we say that the thunks, we're going to send the complete address to work with it, and it's going to be sent used as a variable to the procedure. So even though pass by name looks very powerful, looks amazing, however, it's actually very dangerous. And some situations actually it prevents some stuff from even happening. So consider the procedure that we have here. We want to do a simple procedure swapping. We want to swap two variables, two parameters, x and y together. And you can think of it as a very simple procedure. So we're going to create a temporary variable t. T is going to be equal to x is going to be equal to y, and y is going to be equal to t. So if we have basically a simple example, let's say we have x equal 2 and y equals 3, then basically when we're swapping it, basically y is going to end equal 3 and y is going to end equal 2 and x is going to end up equal 3. Now, let's see the effect of pass by name. Will it actually be able to do such a swapping, even though it looks like it's a very simple procedure? Theoretically, when we say swap A of I and I, it should exactly behave as swapping I and A of I. So whatever order we work with, it should exactly be the same because we want to take the two values and swap them together. However, with the pass by name, does this really happen? Is the swapping exactly the same? So let's look at it here to understand. So let's say that we want to swap R and S, and we're calling the swap procedure. We're calling it with two parameters here, R and S, where R is equal to 1 and S equal to 2. If we want to do the swapping, what we want to have at the end is basically R to be equal to 2, our end thing R equal to 2, and we want to end up with S equal to 1. Okay, so we're going to create T. So T is equal R, so T is going to be equal to 1. R is going to be equal to S, so R is going to be equal to 2. And then S is going to equal to T, so S is going to be equal to 1. Very good. How about something different? How about we want to swap A of I with I? Okay, where A of I is equal to 27 and I is equal to 1. So pay attention to the order. So we send A of I first. So if we return back to our swapping here, we swap t with the first one, which is basically x, and then we take x to be equal y, and then y to be equal to t. Okay, so we are replacing the formulas we have with the actuals. So t is going to be equal to a of I. So t is going to end up being 27. And then a of I is going to be equal I. So basically, remember that we are accessing here a of I. So we are accessing a of 1. So we are accessing a of I, which is a of 1. So we're saying that a of 1 is equal to 1. And then we're setting I to be equal to t. So I is going to be 27. Okay, so I is going to be 27. Now, keep in mind again that I was starting, it was 1 here, so we're accessing a of 1 here. Very good, because, and then the I did not change so far. The t is the one that equal 27, so a of 1 is the one going to be here assigned to 1. Everything is good. I is equal 27. Now, this is a swapping. Swapping should be the other way around, should work as well. So when we do the opposite, I and a of I, it should work the same. We have the same values, I equal 1, and a of I is equal 27, which is a of 1. So let's look at there. T is equal to I. So T is going to be assigned 1. Now I is going to be equal to the value of A of I. So the value of A of 1 is going to be equal to 27. So we're going to take the 27 and we're assigning the I to be equal to 27. Now A of I is going to be equal to the T. So the A of 27. So the I now change it to 27. We're going to take it. So A of 27 is going to be equal to 1. So you see what just happened here, because the A is associated with whatever value of I we have, because we replaced the variables we have here, the formulas, with the actuals. So we replace it with A of I. So whatever I changed it, because we changed I in that step right here, now A of I is being affected. It's now A of 27 instead of trying to access A of 1, which one wanted to do before. So you see that whatever we send to the swap, whether A of I first or send the I first, and when we call the swap procedure right here, it does affect the behavior and it totally mess up the behavior of the swap function. So, and they found actually there is no way to define swap in Algol 60 that works for all the parameters. And it can be proved in mathematical style and mathematical style proof. So it's a big design mistake when a simple common procedure has such surprising property that it's how it's supposed to behave. Now we can make it behave how it is supposed to behave. So returning back to the different parameter passing modes, so passing modes, we have 3 different parameter passing modes. We have the pass by value, which you basically bind to value at time of call. So you only have the value. It preserves the actuals. It does not affect the actuals at all. The actual do not change. And it's inefficient for arrays. And it doesn't have output parameters as well. So you just take it and have a system behavior. Then we have the pass by reference, which is the bind to address at time of call. And it does change the actuals, and it can be used for output, and it's basically efficient for all types of data. The pass by name, it binds to address of thunk at time of call, and so that's different from the reference, the pass by reference. It changes the actuals, similar to pass by reference, and can be used basically for outputs. It is efficient but expensive, and as we have seen, that also we can have some issues with our procedures, like the swapping one not behaving how it is supposed to behave.